So, everybody with me on degrees? Fairly simple to come up with. Radians, on the other hand, give people a lot of trouble. But let's do the same thing for radians. I'm going to use green for my radians. So I'm going to tell you that this very first 30 degrees is equal to pi over 6. Okay, so 30 degrees is equal to pi over 6. So let's do the same thing we just did with the 30, 60, 90, 120, 150, 210. I should have highlighted this one as well. So, if I've got pi over 6, I'm going to skip this little one in between. So right here, this is going to be, I'm going to write everything down, but I'm going to come back and reduce some of these because some of these will reduce. This will be 2 pi over 6. I'm aware that that will reduce, but for the purpose of doing this, I'm going to leave it 2 6 for right now. Then I would have 3 pi over 6. 4 pi over 6. 5 pi over 6. 6 pi over 6. 7 pi over 6. 8 pi over 6. 9 pi over 6. 10 pi over 6. 11 pi over 6. And then the last one would be 12 pi over 6 if we want to write it, but it's kind of optional because we could also just say 0. Could be either one. Okay, now, whenever you do the unit circle quiz, it is fine if you write all of this stuff down, because to me it makes it really easy to label it all, right? You just got to count. 1 pi, 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6. You're just counting as you go around. But on the unit circle quiz, I will require you to reduce them. Okay, so I'm going to reduce them. I'm going to erase the ones that will reduce and replace them. If you just want to like mark yours out and put it next to it, that's fine also if you want to keep that there. But for just to keep it kind of neat, I'm going to erase. So 2 pi over 6, 2 over 6 reduces to 1/3. So this will reduce to pi over 3. For 3 pi over 6, 3 over 6 reduces to 1/2, so that's going to be pi over 2 right there. Four pi over 6 is going to reduce, 4 over 6 reduces to 2/3, so we'll get 2 pi over 6. No, 2 pi over 3, sorry. Five pi over 6, does it reduce? It does not. 6 pi over 6. My 6's just cancel, and I just get a pi, which we kind of already knew that one was pi. Because we know pi equals 180. 7 pi over 6, does it reduce? Nope. 8 pi over 6, what does that reduce to? 4 pi over 3. Nine pi over 6. 3 pi over 2. 10 pi over 6. 5 pi over 3. 11 pi over 6 will not reduce. 12 pi over 6, that's just going to be 2 pi. So, in the end, you want to have all of these reduced values. But it is okay if you need to go around the first time and just go 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6. All right, so that gets almost all of our radian values. We do still have this piece right here, and this one here, here, and here, those little pieces in between. So, what is 45 going to be? If we think of this piece, let's think of pi over 2 right here. This is pi over 2, like that 90-degree angle. Right, so that 90-degree angle, half of it is 45. What is half of pi over 2? Pi over 4. So this angle right here is pi over 4, right? Because if we do pi over 2 and multiply it by 1/2, we will get pi over 4. All right, so that is pi over 4. We can do something similar here that we were doing with the pi over 6's, right? So I'm going to write them over to the side so they're easier to reduce. So we got, this is pi over 4. This would be 2 pi over 4, which we already have reduced to pi over 2, right? Then the next one right here, this one's going to be 3 pi over 4. So right here we'll get 3 pi over 4. Go another 45 degrees, we get 4 pi over 4. But 4 pi over 4 reduces to just pi. Right here, we will have, I'm just going to stick with my purple, we'll have 5 pi over 4, 6 pi over 4, 7 pi over 4, 8 pi over 4. So we'll go back with my green now. So this one right here is 5 pi over 4, and this one right here would be 7 pi over 4. And if we check everything else, 2 pi over 4 reduces to pi over 2. 4 pi over 4 reduces to pi. 6 pi over 4 also reduces to 3 pi over 2. And then 8 pi over 4 is pi over 2. So that gets all of our unit circle values there. So I'm going to erase those purple values because we've got those labeled in green now. All right, so double, triple check and make sure all of your values are correct and in the correct space, because if you're going to study this for your test and for your quiz, you do not want to be studying the wrong thing. So when you fill in this unit circle, you don't have to have it memorized, but you can do what I've just done, sort of like go through it sort of logically, reduce some things there to make sure that you get it right. Now, notice around the edge, you've got all of these little places that look like coordinate points. Looks like we're going to put like a point like 1, 2, or 3, 7 there. So this is only part of your unit circle. This gives you your angles that you're dealing with. We also need to know all of these values around the edge of the unit circle. So that is where our notes are going to come in. So if you guys will look at that sheet that has your notes on it now. We're going to talk about how to get that. But before we talk about that, I need you guys to remind me of some special right triangles. I think we did some. Did we do those in here? I can't remember if we did them in here or not. All right, 30, 60, 90 triangles, special right triangles. The side you want to have is the shortest leg. There's a shortcut that can tell us what the hypotenuse is if we know the shortest leg. Somebody remember it? Did we do that in here? We may not have. It doesn't have pi for this one. It does not have pi. It has roots. Even though hypotenuse does not have roots. So if you know the shortest, so first of all, the angles of the triangle have to be a 30, 60, 90 triangle. If you know the shortest leg, the hypotenuse is going to be twice that. And if you know the shortest leg for this side right here, the longer leg is going to be the square root of 3 times x. There's a chance you may have never done that shortcut. Have you guys seen it before? It is a shortcut because you can figure any of that out just using regular trig like we've done. It is a shortcut I usually try to teach students for the ACT because if you see a 30-degree angle, the reason that we even care about shortcut rules for this is because 30, 60, 90 triangles show up a lot. It's a very common measurement. So if you see a 30-degree angle, then you can just figure this out really quickly. So since I haven't done this before, this is still another side note. We're not doing this part yet. Let me just give you a couple examples. So let's say that we know that this is a 30-degree angle, and we know that this side is 7. Right? Then what would the hypotenuse of this triangle be? It's going to be 14. And what would the longer leg of this triangle be? 7 root 3. All right, so you could find them immediately without having to set up any trig. You could also find it using trig, but you would know it immediately really quickly. What about, I'm going to draw it a different way and give you a different side. What about if I know that this side right here is 10, and I know that this is a 60-degree angle right here. So this time I do not have the shortest leg. It's much easier if you know the shortest leg. This time I have the longer leg. And so if I want to go from the longer leg back to the shorter leg, what would I have to do? It's going to involve a square root, but we're not square rooting it. What? We divide by the square root of 3. Because to get from short leg to long leg, we would multiply by square root of 3. To go backwards, we would divide. So this side right here would be 10 divided by the square root of 3. And then once I know the short leg, what do I have to do to that number to find the hypotenuse? I got to double it. So I got to do 2 times 10 over root 3, which will give me 20 over root 3. And you'll probably see those rationalized sometimes, but it's not really terribly important for what we're doing right here. So we'll do that. You could, if you did rationalize it, this would be 10 root 3 over 3, and this one would be 20 root 3 over 3, because we would just do that by multiplying by that square root of 3 on top and bottom. All right. So this is a side note about 30, 60, 90 triangles. We could use regular trig, but I want to use this because we want exact values in trig. We have to use the calculator and get rounded values. So let's think about the unit circle. So that unit circle that you have on that orange paper there is called the unit circle because it has a radius of 1 unit. Okay, so a radius of 1 unit. So that tells me, we can see it here, right? So from the center to the edge in all directions, the length of that radius right there is 1. All right, you can see that because right here we have the point 1, 1, negative 1, negative 1. All right, so I'm already thinking about my unit circle. Actually, let's do this before we even do this problem right here. Look at that unit circle that you got. All right, so if this is a unit circle, that means that on the x-axis, this value right here is 1. This value right here on the y-axis is 1. This value right here is -1. And this value right here is also -1. So if I want the coordinates of this point right here, what are the coordinates of this point right here at 0 degrees? 1, 0. All right, just think about graphing it. You would go over 1, up 0, right? What are my coordinates at 90 degrees? They would be 0, 1, because from the origin you go over 0, you go up 1, just like graphing points, right? Over here, I've got -1 up 0, so I'd have -1, 0, and here I would have 0, -1. So those 4 points we fill in just like we're graphing those 4 points on those intercepts. But these points here are going to be more difficult to find. So that's what we're going to do right now. So if the radius of this is 1, what I really want to find is I'm going to make myself a triangle right here. I'm going to drop down a line and make that a right triangle. So if I do that, this bottom side of the triangle is the length from 0 to this point over here on the x-axis, right? It's going to give me the x-coordinates, the length of it's going to give us the length that this point right here is from the x-axis, which is going to be my x-coordinate right here. And then vertically, right here, that vertical distance, that is my y-coordinate, because if I went over here, right there, that'd be my distance vertically. Right, so the lengths of these sides will give us the x-coordinate and the y-coordinate of this point right here on the edge of the circle. But that's not doing me much good because I don't have any lengths of that side. Any lengths of the side of the triangle. I don't know any of them. But I should know one of them. What side can I know? The hypotenuse. What's the hypotenuse going to be? It's going to be 1 because that hypotenuse there is also the radius of the circle, right? So this has a length of 1 because any line from the center to the edge is going to have a length of 1. So what we have ourselves here now is a 30, 60, 90 triangle, right? So we know the hypotenuse. What are we going to do to find the shorter leg? That's what you want to look for first. Divide by 2. So for that, we are going to get 1/2. So that means my y-coordinate of this point is going to be 1/2. What do we need to do to find the x-coordinate here? We got short leg. We need to multiply it by the square root of 3. All right, so if we do 1/2 times the square root of 3, it's like square root of 3 over 1. We'll just get square root of 3 over 2. So this x-coordinate here is square root of 3 over 2. That's the length of this side. Okay, so let's go over to our unit circle. Let's add those points right there. So at 30 degrees, we have got the x-coordinate is square root of 3 over 2. The y-coordinate is 1/2. Something that helps me remember that there is that if I think about that triangle, which side is longer, the x or the y? Let me go back to this. So if we look at this triangle here that we drew, which side is longer? That x side right there or the y side? It's going to be the x. Which one is longer, square root of 3 over 2 or 1/2? The square root of 3 over 2, right? So at this point, your x should be longer than your y, so you'll have square root of 3 over 2 and 1/2, because you're going to notice numbers are going to be repeated a lot. So you're going to have very few to actually choose from when you're filling in your unit circle. So if you can remember that one's longer, you need the bigger number to come first there. That'll help you. Okay? All right, so that takes care of our first point, and I will tell you in a minute why in the world we even care about having these points, because it seems very pointless right now. All right, we're just finding points. Just it seems like an exercise for math teachers to torture children with, right? So let's go on to the 45-degree angle. We're not going to have to do every angle in the unit circle. Don't get too worried. We just got 2 more to go, and then we can fill in the rest. So 45, 45, 90 triangle. Okay, if I know that one of these angles here is 45, it means the other also has to be 45 degrees. And if I know either one of the legs, it doesn't matter because this is going to be isosceles, because where we have the same angles, the sides across from those are going to be the same. So if I know either one of the legs, then I can find the hypotenuse by doing x times the square root of 2. So again, this is a shortcut. You could set up trig to do this, but you need a calculator. So this is a shortcut. This one, I have actually used this one myself personally, like at home renovation projects, because that's a square, right? So if you need to find the diagonal of a square, it's always square root of 2 times the length of your side. So this is something that I have used several times. Anytime you need to find diagonal of a square, it's going to come in handy. So this one I find even more helpful to know the shortcut rule than with the 30, 60, 90 as far as like real life goes. But for this, it's going to be helpful as well. So if I make myself a triangle here. So again, I'm going to call this bottom side x and the vertical side right here y. And we know, once again, that the hypotenuse of this triangle is going to be 1 because it's a radius of the circle. So, if I'm looking for the coordinates of this point right here, then I do know, since this is a 45, 45, 90 triangle, that whatever x is, y is going to be the same. So my 2 coordinates should be the same here. If I get 3, I'll have 3, 3. Or if I get square root of 5 over 7, I'll have square root of 5 over 7, square root of 5 over 7. They'll be the same. All right, so to go from the hypotenuse to one of these sides, what do I need to do? Divide by the square root of 2. So when I do that, 1 divided by the square root of 2, I'm going to rationalize this just because mathematicians decided that that's what should be done. So we'll get square root of 2 over 2. So that is the length for my x and also my y, because they're going to be the same. So I'll have square root of 2 over 2 is my x coordinate, and square root of 2 over 2 is my y coordinate. So that is for 45 degrees. So let's go over to our unit circle and let's add that in. So we got square root of 2 over 2 and square root of 2 over 2. Okay, we're really almost done, even though it seems like there's a lot to go. All right, last one that we're going to do this way. If I drop down a line here, we're still going to call this side right here x because it is horizontal. We're going to call this side right here y. Okay, we still know that the hypotenuse is 1. So this time to find the short leg, which is now my x, all I have to do is divide by 2. So this x right here is going to be 1/2. So that's going to be our x coordinate. And then to find the y, we're just going to multiply by the square root of 3. So that is going to give us square root of 3 over 2. So notice this is almost like our 30-degree angle, except for our sides have switched now, right? We've got the 1/2 is first, and then the square root of 3 is second. I remember this because that x is shorter and the y is taller here. So the lower number has to go first, the higher one has to go second. So we got 1/2 and square root of 3 here. So let's go to our unit circle. We just found this point right here to be 1/2 square root of 3 over 2. All right, if you can fill in your degrees and your radians, and you know this much of the unit circle, you should be able to do the rest of the unit circle. Because we know in this quadrant, first quadrant, we're going to have a positive and a positive. For the second quadrant, we'll have a negative x value, but a positive y value. For the third quadrant, we'll have negative, negative. And for the fourth quadrant, we'll have positive, negative. So this is going to make it very simple for us to fill this in, because all we have to do is think about reflecting these points, right? And then changing the sign of the coordinate that needs to be changed. So this point right here, 1/2 square root of 3 over 2, it's going to go right here. But in the second quadrant, the x coordinate needs to be negative, so I'm going to make that 1/2 negative there. Same thing for our square root of 2 over 2 and our square root of 2 over 2. It just transfers over here. We're reflecting it over that y-axis right here, which means our x coordinate will now be negative. Same thing here, square root of 3 over 2, 1/2, but now our x coordinate is negative. Let's think about the fourth quadrant next. I'm going to take this point right here, square root of 3 over 2, 1/2. I'm flipping it right here, square root of 3 over 2, 1/2. But my y coordinate needs to be negative. This one will be square root of 2 over 2 and square root of 2 over 2. But again, y coordinate is negative. And then here I've got 1/2 square root of 3 over 2, y coordinate is negative. And then for your last quadrant here, for the third quadrant, you can either think about flipping this over here or this number down here. It really doesn't matter which one you're thinking about. But you'll have that square root of 3 over 2 and the 1/2. Both coordinates need to be negative. Square root of 2 over 2 and square root of 2 over 2. Both coordinates need to be negative. And 1/2 square root of 3 over 2. Both coordinates are negative there. And so that is your unit circle. That's what you have to have memorized. It looks really complicated, especially if I had just like handed it to you and been like, memorize this, right? But I wanted to go through the process of filling it in with you so you kind of understood where pieces come from, or at least hopefully a little bit, to know that you do need to have it memorized, but it's not so much as just memorizing without any reason whatsoever. Because if you just try to memorize, there's like 64 numbers on here that you have to memorize, and it's a lot to remember in each place. But use your symmetry, use what you know about angles to help you fill that in. So let's talk about why in the world we're doing this. Why do we have to do this? We're going to skip this slide right here because we've already converted radians. So why in the world are we going to do this? And so it all comes from I need a slide for this actually. It's not a slide, I'm going to put it down here at the bottom. So you can add this, if you want to add this, actually we're going to write on this one because we're going to skip this slide right here because we've already done that on that other paper. And I think some days I do it separate days and I want to practice it a little bit more. But I think we're good for today. So if we think about just one of those triangles from our circle, right? Here. This is my x side. This is my y side. I know my hypotenuse is 1. Right? And so my coordinates right here are x, y. Those are my coordinates of this graph. I'm just going to call this angle theta. So it could be any angle. So if I want to find sine of theta with this triangle, right? That could be a 30-degree angle, 45, really anything. If I want to find sine, sine would be opposite, which in this case is going to be y, over hypotenuse. What's our hypotenuse here? It's just 1. So sine of theta is going to equal y. So I do not have it at the top of my unit circle that I put here, but at the top of yours, you've got an x equals and a y equals. There you got some blanks for x equals and y equals on that orange one. So y is going to equal sine of theta. So that y coordinate is your sine of theta, right? Oh, wrong way. And so if we think about looking at cosine of theta, that would be adjacent over hypotenuse, which would be x over 1. So that tells me cosine of theta just equals x. It is my x coordinate. So there at that line, we're going to put cosine. So if I want to know sine of 30 degrees, right, I could type it into my calculator, but I realize we pretty much always have calculators with us these days. We also pretty much always have calculators that can do sine, cosine, and tangent. That, like, in my day, that probably was not the case necessarily, because you would have needed, like, to be carrying a TI-84 around in your purse for that to happen. But your calculators on your phones will still do sine and cosine, right? So this unit circle certainly was much more necessary and valuable in times whenever there were not calculators that could do sine, cosine, and tangent. Because we know if you ever have sine of 30 degrees, it is going to equal 1/2. It is the y coordinate of that point on the unit circle. And that is always the case. Now, if you were even like 100 years ago and you didn't have a calculator, or really probably 50 or 60 years ago, you probably were not, even like my parents' age, they just basically used like 4-function calculators. They didn't have the fancy ones, right? So even 50 or 60 years ago, you would not have that stuff stored in your calculator. So go way, way, way back before there were calculators, whenever you were ancient mathematicians, you relied on this unit circle because you needed it for your values of sine and cosine. And there are other methods, which we're not going to go into, where you can find other angles in between here, so you could have some other ones that you could know the values for. But this would be difficult. If we went back like 60 years ago to like probably my parents, your grandparents sort of age, then if they were doing trig, which first of all was probably not required for graduation at that point, so there's a chance they just never did it at all. But if they did do trig, they would have had a table that would have looked like this. Let's see if I can find one. Let's see if I can find one. I bet there's not even an extensive one available. Here's one, I think. Yeah, you would have a table that would have looked like this. That would have given you your degree measures, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And if you wanted to know the sine of 30 degrees, you can see right there it's 0.5. You would have had to use that table to look this up. So if you needed to know the sine of 16 degrees, you would have had to look that up. Now you can just type it into your calculator today, which is obviously way better. So we're not going to go back to the days of using this. And we're not going to extensively go back to the days of the unit circle even before that, because we do have a calculator. So when we're doing application problems, we're not going to go back to that. But the unit circle is valuable, and the reason that we still teach the unit circle is because this is going to help us relate to how we graph trig functions. And once we graph trig functions, then we can see where trig functions can actually apply in situations that have nothing to do with triangles at all. And so it's kind of cool to see that connection. So that's the reason that we do the unit circle, is for that connection between these. Because normally we're just looking at a triangle, and the biggest angle we can have in a triangle is, we can't have any angles over 180 degrees, right? And probably not even that close to 180 degrees. So that's the most you can look at. But if we look at the unit circle, we can go all the way from 0 to 360. And we can actually go further than that, because we could continue rotating, right? We could go around again and get 720. And we could go around again and get whatever that is there. What is it, 1080? Is that the next one? No. After 720, is that 1080? So you can keep going around and around and around and around, and it's going to produce these values over and over and over again. So that's the reason that we're doing this. Let's fill these last few things in, and then we'll finish up doing this at the beginning of class tomorrow. So tangent, we already knew tangent was opposite over adjacent, but there's another identity we're going to learn for tangent. Tangent of theta equals sine theta over cosine of theta. And we don't have time to today, but on Monday I'll show you why. Okay. Secant of theta is 1 over cosine of theta. Cosecant of theta is 1 over sine of theta, and cotangent of theta is cosine theta over sine theta. I'll talk more about why that is and what we're going to use it for here in a minute, but, or not in a minute, on Monday.